Why are airplane windows rounded instead of square? Seriously, think about it. Your bedroom window can be a rectangle. Your TV can be a giant rectangle. But when you climb 35,000 feet into the sky, suddenly the airplane decides that rectangles are a terrible idea. Why? The real reason has to do with something you can't see, and a mistake in early jet aviation that taught engineers a very serious lesson. And once you understand it, you're going to look at every airplane window differently. Okay, so let's start with the obvious question. If square windows work perfectly well in houses, why can't an airplane just have square window? I mean, square is easy. 4 straight sides, 4 corners, done. Engineers love efficiency. Well, not when those 4 corners are being bullied by thousands of pounds of pressure. Because an airplane cabin isn't just a room with wings, it's a pressurized container. When you're cruising high above the ground, the air outside the airplane is much thinner than the air you need to comfortably breathe. So the aircraft keeps the cabin at a higher pressure than the surrounding atmosphere. That means there is a pressure difference between the inside and the outside. And that pressure difference is constantly trying to push the fuselage outward. Basically, the airplane is up there going, "Guys, I'm holding the air in. Please don't make this weird." And the structure has to deal with the pressure every single flight. Every time the plane climbs, the cabin gets pressurized. Every time it lands, the pressure comes back down. Over and over, flight after flight, circle after circle. And that's where the shape of a window suddenly becomes very important. Imagine stretching a rubber sheet. Now imagine pushing on that sheet. The force can spread around a smooth, curved opening. But now cut a square hole. Those sharp corners interrupt the way the force travels through the material, and the stress becomes concentrated there. Stress concentration, that's the key. Here is an easy way to picture it. Take a piece of paper. If you start a tear along the edge, you can usually rip it pretty easily. But if you have a tiny cut, that little cut gives the tear somewhere to concentrate. And suddenly, the tear wants to keep going. Sharp corners can create a similar problem in aircraft structure. Not because an airplane is made of paper, although that would make turbulence considerably more exciting. No, because materials under repeated loads can develop fatigue. And this is the part that makes the whole thing fascinating. Metal doesn't have to break the first time you stress it. It can survive one load and another and another. But repeated stress can eventually cause tiny cracks to form and grow. That's material fatigue. And airplanes are very good at giving structures repeated circle. So engineers don't just ask, "Can this airplane survive today's flight?" They have to ask, what happens after thousands of flights? And here's where airplane window history gets serious. In the early 1950s, the de Havilland Comet became the world's first pressurized civilian jet transport. It was revolutionary. It flew higher, it flew faster, and it offered passengers something that was still relatively new, a pressurized jet cabin. But there was a problem. The windows were relatively squarish, and those corners created areas of very high stress. Between 1953 and 1954, several comets suffered catastrophic in-flight breakups. Investigators eventually discovered that fatigue cracking in the pressurized fuselage was a critical part of what happened. The stress concentration around the squarish window area were much higher than expected, and those tiny cracks could grow under repeated pressurization circle. The FAA's historical investigation describes the squarish windows and frames as creating higher stress concentration with fatigue cracks developing around the corners. So this wasn't just maybe rounded windows look nicer. It was structural engineering. But here's an especially interesting part. Investigators didn't just stare at the wreckage and gaze. They built tests to reproduce what was happening to the aircraft. And one full-scale Comet fuselage was repeatedly pressurized. Eventually, the fuselage failed at the corner of a squarish window. That was a huge clue, because now engineers could see the problem happening in front of them. The geometry was concentrating stress at the corners. The repeated pressure circle were turning that stress into a fatigue problem. Now we can finally answer the original question. A curved window doesn't have those abrupt 90-degree corners. Instead, the stress can flow more smoothly around the opening. Think about traffic. If 4 roads all slam into one tiny intersection, things get crowded. But if the roads curve smoothly around a bend, the movement is much more gradual. Aircraft structure isn't literally moving traffic, but the analogy helps. Now you might be thinking, okay Zeno, if curves are good, why not make an airplane window perfectly circular? And you actually do see plenty of curvature. But airplane windows are generally shaped more like rounded rectangles or ovals rather than perfect circles. The exact shape depends on the aircraft design, structure, manufacturing, visibility, requirements, and other engineering considerations. The important structural idea isn't make it a circle at all costs. It's avoid sharp corners where stress can concentrate. But there is another little detail people miss. When you look through an airplane window, you are not looking directly through a simple hole punched into the metal. The window assembly is part of a larger structural system, and the surrounding fuselage has to carry loads around that opening. So the shape of the opening matters, the frame matters, the materials matters, the thickness matters, and the way everything is attached matters. And this is why something as tiny as an airplane window can teach you something much bigger about engineering. Whenever you cut a hole into a structure, you've changed how force travels through it. That means engineers have to think about where those forces go, where they concentrate, and what happens after the structure experiences the same load thousands and thousands of times. That's why aircraft design isn't just about making something strong. It's about making something strong and predictable for a very, very long time. The Comet accident changed aviation engineering. They helped demonstrate just how important fatigue and stress concentration are in pressurized aircraft structures. The aviation industry developed a much deeper understanding of how repeated loading affects aircraft. And the modern aircraft are designed, tested, inspected, and certified with structural fatigue and damage tolerance as major considerations. So every time you look at that little rounded rectangle beside your seat, you're looking at the result of decades of engineering lesson. And now here's the part I want you to remember. A square window isn't automatically going to make an airplane fall apart. The problem is what sharp corners do to stress. And when you are dealing with a pressurized aircraft, that stress can be repeated again and again and again until a tiny problem becomes a very big problem. A rounded shape helps reduce those sharp stress concentrations by allowing the load to distribute more smoothly around the opening. And that's why the shape of something you probably never think about is actually doing a very important job. That little rounded rectangle is basically engineering saying, I would rather not have a crack develop here. Honestly, fair enough. And if you want more everyday things explained before you spend another 20 years staring at them without asking why, you know where to find me. Hit that subscribe button and see you in the next discovery. This is Zeno IQ.